Welcome to The Explainer. Today, we're tackling a massive, high-stakes engineering challenge from one of the biggest tech giants in the world, Uber. Imagine a financial engine, specifically their core payments platform called Gulfstream, which processes millions of transactions daily, suddenly hitting a physical speed limit. And we're not just talking about a simple software bug here. It's a fundamental physics problem regarding how data actually moves. So today, we're going to explore exactly how Uber's engineering team successfully shattered these physical limits. 24 hours. I mean, think about how lightning fast an Uber ride feels on your phone. But behind the scenes, massive fleet and marketplace operators were completely overwhelming Uber's SOX-compliant Gulfstream system. They were initiating tens of thousands of daily bulk financial adjustments against a single user account. Because of this massive, unrelenting surge, which should have been an almost instant financial update, was taking a staggering 21 to 24 hours to complete, actually a full day just to settle the math. So the core question of our explainer today is, how do you actually compress 24 hours of financial data processing into just a few minutes? And remember, we aren't talking about casually compressing a photo where losing a few pixels is totally fine. This is a SOX-compliant double-entry accounting system. The basic accounting principle here is that money flows between accounts without creation or destruction. You can't simply skip steps to save time. Every single penny must have a perfectly immutable audit trail. The stakes for getting this wrong are absolutely astronomical.
Okay, let's dive into part one, the hot account problem, when success breaks the system.
To really understand this breakdown, we've got to look at what engineers call a hot account. A hot account is essentially an account experiencing an extreme traffic burst that completely overwhelms the system's standard processing limit. Uber's baseline limit was about 3 to 4 update operations per second per account. Now, that sounds totally fine for you or me taking a single ride. But what if you're a massive fleet operator, or say an Uber for Business client subsidizing thousands of rides in a specific region? You're hitting that account with hundreds of thousands of transactions. These massive payment bursts create intense systemic bottlenecks that bring the entire processing pipeline to a painful crawl. Moving on to part two, the sequential speed limit, the physics of the bottleneck. The traditional approach they were using was sequential. Step 1, read the account state. Step 2, check the processing history. Step 3, actually update the account. And Step 4, write the mandatory audit logs. Now, I want you to imagine you're walking to the grocery store. You walk there, buy one single apple, walk all the way home and put it on the counter. Then you literally walk all the way back to the store just for a banana, walk back home and put it on the counter. Imagine repeating that entire trip for every single item on a grocery list of hundreds of thousands of items. That was Uber's data pipeline in a nutshell. And here's the brutal math of that grocery trip. Each of those sequential operations took a total latency of 130 to 370 milliseconds to complete. If you need to hit a target of over 30 operations per second just to clear out the massive backlog of a hot account, but one single operation takes up to a third of a second, well, it's mathematically impossible to achieve that through sequential processing. You literally cannot bend the physics of network latency. They needed a totally new paradigm. Which brings us to part 3. The sub-second batch solution, a paradigm shift in processing. Well, the engineers had a massive realization here. Compute time wasn't the actual issue. The real villain, that was the round-trip travel time to the database. They needed to batch these updates to, amortize the latency costs. Standard industry heavyweights like Apache Kafka were actually rejected. Why? Because client-side batching and consumer delays inherently add about 1 to 2 seconds of latency. And Uber has a soft limit of 1 second for real-time operations, like putting an authorization hold on your credit card. So they pivoted. They moved to Redis batching using ultra-fast, 250 millisecond time-bounded windows. It's short enough for real-time responsiveness, but long enough to group meaningful amounts of data together. And that brings us to the golden rule. No matter how many operations are squeezed into that 250 millisecond window, whether it's 5 or 50, there is strictly only one read and one write that happens to the user account store per batch. Going back to our analogy, they finally invented the shopping cart. You put all your groceries in the cart and you make exactly one trip to the checkout counter. This was the brilliant, latency-killing insights that changed everything. Part 4, building the batch engine, the 3-part architecture. So 3 distinct components make this whole vision a reality. First, you have the batch creator, acting as the entry point. It utilizes a Redis cluster,
thanks to its sub-millisecond latency, to group all incoming operations into those strict 250 millisecond windows. Next is the batch process service. This is the core engine. It reads the account state just once, applies all operations super fast in memory, and uses what's called optimistic locking to ensure everything is perfectly consistent. Finally, we have the batch post-processing service. This is completely decoupled from the main path, handling the incredibly vital but time-consuming audit logs asynchronously.
But here's the catch. When you move this incredibly fast, you hit completely unexpected walls. They suddenly realized all these fast transactions were generating so many traditional audit logs that the user accounts were going to rapidly exceed their physical storage limits. So they innovated again and developed the micro UAC. It's a newly developed audit log format compressed to under 100 bytes. It's an ingenious workaround that proves a really key lesson in system design. When you radically increase your speed and throughput, you absolutely must shrink your digital footprint.
Part 5, Shadowing and Stress Testing. Trial by fire. Now, you absolutely cannot just flip a switch on a massive, SOX-compliant financial platform without absolute, undeniable certainty. I mean, a single bug in a high-throughput pipeline could lead to systemic data corruption. So, to guarantee zero errors, Uber used a really effective technique called shadowing. They basically routed a copy of live production traffic silently into the new system without letting it actually affect the real-world environment. They ran the old legacy system and the new batch system in parallel, rigorously validating two things: completeness and correctness. Completeness asks, is all the work actually done? Like, did every log persist without any messy, dangling state left behind? Correctness, on the other hand, asks, is the math absolutely perfect? They check if the legacy account A exactly matched the newly processed account B. The pass criteria? Zero margin for error. The final states had to be perfectly identical.
But being perfectly correct under normal, everyday conditions, that wasn't enough. To truly find this new system's breaking point, they artificially amplified that live shadow traffic by a staggering 15 times. They hammered the new batching engine with 15 times the highest peak volume Uber sees in the real world just to simulate massive unexpected bursts. They wanted to sniff out any hidden bottlenecks, things like database connection pooling or CPU saturation, making sure that no matter what kind of extreme demand hit the system, it wouldn't even flinch.
And finally, Part 6, From Hours to Minutes, the payoff.
The sheer scale of this victory is just incredible. The system now processes financial operations that previously took 21 to 24 hours in just minutes. We're talking about effective latencies dropping to between 8 to 20 milliseconds per operation within a batch. By completely obliterating that old sequential bottleneck, Uber didn't just make an old process faster, they unlocked entirely new business capabilities for their largest fleet and marketplace clients that were previously considered technologically impossible due to systemic lag.
Which leaves us with a really fascinating thought to wrap up our explainer today. If a physical speed limit, a literal mathematical impossibility due to network latency, can be completely broken by simply changing how data travels together in a 250 millisecond window, what other impossible bottlenecks in your business or projects are just waiting for a paradigm shift? Are you still carrying groceries one item at a time? Start looking for your own grocery cart solutions to extreme scaling challenges. Thank you so much for joining me to explore this incredible engineering feat. And remember to keep asking those big questions.